In this lecture we will start with different logic families and the internal architecture of those. So let us start with diode logic. Or DL. So specifically for now we will try to understand how OR gate can be built using DL. So OR gate using DL. So let us first construct the circuit. So circuit looks something like this. We have two resistors with two diodes. These are connected with each other, and we have this resistor here, and these are the inputs V1 and V2, and this is the output V out. Let us call this diode D1 and this one as D2, and the value of resistor should be 1 kilo ohm here and also 1 kilo ohm here. This is 10 kilo ohm. Okay. So this is the circuit. So this is a OR gate, an OR gate built with diode logic family. So first of all, let us look at the truth table. So this is the truth table. V1, V2 are the input and V out is the output. So very easily we can understand how it should look like. So we have 4 possible cases for OR gate because we have 2 inputs, right? And the output should be what? Whenever one of the inputs is 1, then we are going to get 1. So this is 0, this is 1, 1, and the output is 1, right? So these are the 4 possible cases we have, and we have to prove our circuit that it works properly for all of the cases, all 4 cases. So let us start with that. So let us start with case 1. For case 1, we are going to look at this one, right? So V1 should be what? 0 volt, because all of the things we are seeing here, these are represented by voltage. That means logic 0 should be close to 0 voltage and logic 1 means should be close to 5 volt. Even though these kind of logic families, diode logic families, was never used commercially, these were never implemented commercially, just for educational purpose. So we don't have any specific defined logic levels for this particular type of logic family, but still we can understand that initially we talked about the fact that whenever we are talking about logic 1, it should be closer to 5 volt, right? And whenever we are talking about logic 0, it should be closer to 0 volt. So in this way we will try to understand how our circuit is working. So for case 1, V1 and V2, both of them are 0 volt, right? So just try to understand that whenever both of the inputs are at 0 voltage, obviously these diodes, 2 diodes, will not be conducting. These are not forward biased, am I right? So that means this is reverse biased, this is also reverse biased. Let us write it here. D1 is reverse biased and D2 is also reverse biased. If they are reverse biased, that means what? No current is flowing through this path and also no current is flowing through this path. So whatever we are getting is from this path, and no voltage is here, so no current is flowing through this path. So we are directly going to get this ground voltage, that means 0 voltage for V out. So output V out should be what? 0 volt. So first condition is fulfilled. Whenever we have both of the inputs as 0 voltage, the output should also be 0 voltage. Now let us look at case 2. For case 2, V1 should be at 0 voltage and V2 should be at 5 volt, right? And in that case, what should happen? As V1 is at 0 voltage, obviously just like before, D1 should be turned off or reverse biased. And for V2, because we have provided 5 volt and this thing is connected with ground, so obviously at this point the anode is connected with a higher voltage compared to the cathode, so D2 should be, we can assume that D2 is forward biased. So let us write that D1 is reverse biased and D2 is forward biased. If this is the case, can we simplify this circuit? Can we draw a equivalent circuit that represents this whole thing whenever we have case 2? To do that, what we can do, we can omit this path because this is actually open circuited because of this reverse bias diode. So we can just take the path of this one, then try to write an equivalent circuit. So to do that, first of all we have to draw this voltage source which is 5 volt, right? So this is 5 volt voltage source which is representing this one, V2. Then from there we have this resistance of 1 kilo ohm. Then D2. Everywhere in this kind of analysis we will try to use constant voltage drop model. That means all the forward biased diodes should be replaced by 0.7 volt for silicon diode. So we are going to do that. So here we are going to use a voltage source like this, and the voltage of that voltage source should be 0.7 volt. And then finally we can just write all the other portions just like before. So 10k resistance here, then to ground, so 10k. And here we are going to get the output V out. So now the current that is flowing through this whole path, we can call that capital I, and we have to find out the value of I to find out the value of V out. Let us try to do that. So to find out the value of I, what we can do, we can take a KVL in this path. So it should be what, -5 plus I multiplied with the value of resistance which is 1 kilo ohm, then 0.7 volt. Then we are coming here, so I current is flowing, no current is flowing through this path because this is open circuited, so I will go through this path to ground. So we can write plus I multiplied with 10k, then this should be equal to 0. So from that we have to find out the value of I. So let us try to find out the value of I. So we have 11k multiplied with I, and all the things can go in this path. So then we are going to get the value of I. I should be equal to what, 4.3 divided by 11k ohm, right? Which should be equal to what, 0.39 milliampere, right? This is the amount of current. So if we got that value, now we can find out the value of V out. So V out should be equal to what here, V out should be equal to the current going through that multiplied with the resistance value. So V out is equal to the value of I multiplied with 10k. So 0.39 milliampere multiplied with 10k ohm. So we are going to get what, 3.9 volt. So you see the voltage we are getting close to 5 volt, we can say, because these are primitive model. We cannot expect very good voltage that is very close to 5 volt, but we can say that this is somewhat close to 5 volt. So that's why we can say the case here, case 2, this is also proved. Whenever we have V1 is equal to 0 volt and V2 is equal to 5 volt, then we are going to get a logic high state which is actually showing us 3.9 volt. If we talk about case 3, which is V1 should be at a logic high condition 5 volt and V2 should be at 0 volt, this is exactly identical condition as this one, right? Because we are just interchanging the voltages here. All of the circuits should be exactly like this one. So for that case, I mean, whenever we have what, whenever we have case 3, and case 3 means V1 should be 5 volt and V2 should be 0 volt, at that condition D1 should be what? Forward biased, and D2 should be reverse biased. But after doing all the analysis, we are going to see that for this case also V out should give us a value of 3.9 volt, which is actually can be considered as logic 1. So case 3 also verified. Now we will look at the last condition, case 4, which is whenever both of the inputs V1 and V2 are at high logic. So let us try to do that. So for case 4, V1 should be 5 volt, V2 should be 5 volt as well, and because both of them are at logic high condition, so we are going to get a high voltage here at the anode compared to cathode, and because of that both of the diodes will be forward biased. So D1 should be forward biased FB, and D2 should also be forward biased. Now how the equivalent circuit should look like, let us try to understand that. So we can directly write something like that. So because we have two different voltage sources here which are actually 5 volts, so we can draw these two here, and we have this ground here. Okay, so this is 5 volt, again this is also 5 volt. Then we are going to get the two resistances, this one and this one, and because both of the diodes are forward biased, we can replace those using a voltage source of 0.7 volt here. So both of them are replaced by 0.7 volt. Yeah, then everything should look exactly like before. So we have this resistance of 10k ohm, and we have got the output from V out. So yeah, this is 1k, and this is also 1k ohm, right? Now the question is, how can we simplify this particular circuit, equivalent circuit, right? To understand that, you have to understand, like in a circuit, whenever we have multiple grounds, we can actually connect all of them together because these are, you know, at a same voltage level. That's why we can think of them as same node, right? So if we have a big circuit like that, and we have one ground coming from here, maybe another ground coming from here, another ground coming from here, different things can be here. We are not you know, thinking about those things, but multiple grounds are coming out of the circuit. Like here we have 3 different grounds. These are actually can be considered as shorted, connected together, because they are in the same voltage level, or all of them are can be considered as same node. So same concept can be applied here also. Like if you think about this node here, let us try to use blue color, like this point here and this point here, both of the points are representing 5 volt, right? So they can be considered as the same node, and that means we can directly connect them together if we want, and same thing can be done here also, right? So let us try to resolve this problem first. Like if both of them are actually the same voltage at this point, that means both of the voltages are in parallel with each other and they have the same voltage. Now whenever we have two different voltages with same voltage level in parallel to each other, we can just you know, replace them with one voltage source. Like we have two different voltage sources, we can just replace them using just one. Why is that? Let us try to understand. Okay, so what we are going to do, we are going to, you know, connect with one voltage source here, which is 5 volt, because whenever we have multiple voltage sources of same value parallel to each other, that is just increasing the capacity of that battery or that voltage source. Like whenever we are using any kind of mobile phone, the capacity is written like 5000 milliampere hour. So whenever you have multiple voltage sources in parallel to each other. Let's say we have 12 volt voltage sources, and like that we have 5 different voltage sources. If we connect them together in parallel to each other, that is just increasing the capacity of that voltage source or that battery, so that the load, or in our case the mobile phone, can be run for longer time. That's it. But generally the voltage level of the whole device, of the voltage source itself, it is not changing. It is still 12 volt. So for our case here, we are not considering anything about the capacity of the voltage source. We are just trying to analyze the circuit, how much voltage we are getting at the output. That's why if we have two different voltage sources in parallel to each other, which are equal to each other, like we had here 5 volt, that means we can just replace those using just one voltage source of 5 volt. The similar concept can be used here also. Like you can see, if I think about what is the voltage here at this node, let us just assume that the voltage is Vx. That means at this point we are going to get a node voltage of Vx plus 0.7 volt. And similar voltage can also be seen here at this point, Vx plus 0.7. What that means, both of the nodes are the same nodes and they can be shorted with each other. And if we do that, again we are getting the same condition, like we have two voltages with same value in parallel to each other. We can just replace those using one voltage source. So let us try to do that. So we have connected the two resistance in parallel to each other, and actually these two parallel resistance, if we try to simplify into one resistance, that will be 500 ohm, because if we have two resistance of similar value parallel to each other, then the resultant or equivalent resistance of that particular configuration will be half of the resistance of each resistor, right? So that means 500 ohm should be the situation here. So let us try to omit this portion and directly write here 500 ohm. So this is the finalized circuit we have here, and we can try to find out the current that is going through the circuit, which is being called I. So capital I. So let us try to find out the value. So if we just apply KVL here again, we are going to find -5 for this one, then I 500 ohm multiplied with I, then 0.7 volt, and then the current is going through here. That means 10k multiplied with I in total equals to 0. So let us try to find out the value of I. So I multiplied with what? 10,500 ohm, and all the things here will be going to the right side. Then we are going to get the value of I, which is 4.3 divided by 10,500. So this is our final value. So we are getting 0.409. Let us call that 0.41. So 0.41 milliampere is the current we are getting, and from that we can also find out the value of voltage, right? So to find out the voltage, V out is equal to what? I multiplied with 10k. So I is 0.41 milliampere multiplied with 10k ohm resistance. So the final value should be what? 4.1 volt. So for this case also, the value we are getting here is very close to, not very close to, I shouldn't say that this is very close to 5 volt, but somewhat close to 5 volt, and that is why we can consider that the output we are getting is logic 1. So for the last case, if both of the voltages at input is 5 volt, we are getting logic high because we are getting 4.1 volt. So for all of the cases, this particular circuit is actually giving us proper output for it to be a OR gate. Okay, next we are going to build an AND gate using DL, diode logic. So first of all, let us build the circuit, draw the circuit. The values of resistance here is 1 kilo ohm and 1 kilo ohm here, D1 and D2. So this is the circuit for AND gate using DL. So here also let us first try to build or understand the truth table. So V1 V2 and the output is V out. So 0 0 0 1 1 0 and 1 1 are the possible input values we have, and for those cases we know that whenever only all of the voltages at input is logic high, then we are going to get a logic high output for all of the cases except that should get logic 0. So this is the truth table we have got, right? And for all of the cases we have to verify that this circuit works properly. So case 1, for case 1 V1 should be equal to 0 volt, V2 should be 0 volt, and if both of them are 0 volt, that means what? You see 5 volt is coming from the supply here, then we have resistance and these are going through the diodes, and if we have lower voltage at these two inputs of 0 volt, that means what? We can assume initially that both of the diodes are forward biased because this particular node will be at a higher potential compared to this one. As a result, both of them are short circuited, and we can actually build or draw an equivalent circuit to represent the condition what we are getting. So let us try to do that. So basically what is happening, you are giving 0 volt at both of the cases, and because of that D1 is forward biased and D2 is also forward biased, and if that is the condition, then the equivalent circuit should look something like this. We will see ground is connected here to represent the 0 voltage here, then we have this resistor here, another ground for the V2, and we are going to get this resistor, then D1 D2 both of them are actually forward biased. So that means what? So we are going to see a condition like that. Both of them are 0.7 volt, and all of them are actually connected with what? 5 volt with 10k. So let us just draw it here. This is 5 volt, right? And then we are going to get the output from here, V out, right? So how can we simplify this? We can again take the assumption that these two nodes here, they have the same potential because of these two voltage source being similar voltages. So that means we can just connect it here, and you can just omit these two voltage sources with just one, right? So let us try to do that. We will try to simplify that. Also, you see both of the grounds can be shorted together. That can be done. So let us try to do that as well. this is connected here. Oh, these values should be 1 kilo ohm, and this one also 1 kilo ohm, right? And this is connected here properly. So again we can simplify these two resistance using just one. So the resultant value should be what? 500 ohm, just like before. So let us write the value here, 500 ohm. So now we have to find out what is the current that is going through this path, that is I, right? So to do that we can just use KVL. So start from here, so minus 5 volt, then we have this resistance value of 10k, right? 10k. So 10k multiplied with I, then 0.7, then 500 ohm multiplied with the current, so 500 multiplied with current, then we have got ground. So that means this is the result, right? So I multiplied with 10,500 and 5, and this thing should be at the right side, so that means 5 minus 0.7. so just like before, again we are getting 4.3 divided by 10,500. So the value is 0.409 milliampere, or we can just simplify that to 4.1 milliampere, and then we can find out the value of V out. So V out should be what? V out here at this node can be found out using the voltage we are getting here, then minus the voltage drop here, that will be V out. Or also we can find out what is the voltage we are getting here, this voltage source including this voltage drop here. Both of the things are correct, right? So let us try to do this one. So that means V out should be 5 minus the voltage drop. So I is equal to 4.41 milliampere multiplied with 10k ohm. So that value is equal to what? 0.9 volt, right? So this is closer to 0 volt. So that means we can say output is giving us logic 0 for the condition whenever we have V1 is equal to 0 volt, V2 is equal to 0 volt. So first condition is fulfilled. So now for case 2. For case 2, V1 should be 0 volt, V2 should be 5 volt. And for that case, because V1 is at 0 volt, so 5 volt is higher compared to this V1, at that condition D1 will be forward biased. But for this case, V2 is 5 volt, also we are getting at this node 5 volt almost. Maybe there can be some current flow because of the forward biased condition here, but still we need because V2 is 5 volt, we need at least 5.7 volt at this node for this diode to be forward bias. So this is never possible. That means we can assume D2 is reverse biased. So D2 portion can be totally omitted whenever we try to build an equivalent circuit or simplified circuit of this condition, case 2 condition. So first let us write D1 should be what? Forward biased, and D2 should be reverse bias. So then the equivalent circuit should look something like this. We will have the ground here for D1, V1 here, then we will have this resistance of 1 kilo ohm, then we have D1 which is what, like this, and then this resistance with the voltage source, or we can also draw it like this if we want, just like batteries. So this is 5 volt, this is 10k ohm, and here we are going to get the output V out. Now we can use our KVL to find out the current that is going through this path, right? So to do that, what? First of all, minus 5, then I current is flowing through 10k, so I multiplied with 10k, then this voltage source value should be 0.7, so plus 0.7, then 1k multiplied with the current itself I. So equals to 0. So if that is the condition, what should be the value of I? Again 11k multiplied with I equals to 4.3. that means I should be equal to 4.3 divided by 11k ohm, right? So the value should be what? 3.9 milliampere. So 0.39 milliampere, sorry, this is the value. And based on that we can also find out the value of V out. V out should be what? This voltage minus the voltage drop here. So V out should be equal to 5 minus I, which is 0.39 milliampere multiplied with this 10k ohm. So 10k ohm. So what? It should be 1.1 volt. Again we are getting the condition, a value of voltage which is very close, not very close, closer to 0 volt. So we can say this is logic 0 condition. So second condition fulfilled. Now for the third condition also, third case, we can see that this condition is identical to the second one because just the input pins are interchanged, that's it. And then finally the last one is both of them are given as 5 volt. If that is the condition, what should happen? Case 4, right? For case 4, because both of them are at higher voltage, V1 is equal to 5 volt, V2 is equal to 5 volt. Obviously at this node we need at least 5.7 volt or greater than that voltage for D1 or D2 to be forward biased. This is not possible, so that means D1 is reverse bias and D2 is also reversed bias. If both of them are reverse bias, that means whole of this circuit, whole of this portion is open circuited. So V out will get the voltage from direct 5 volt here, and this thing is open circuited, so actually no current is flowing from this path to that path, so no voltage drop here. Direct 5 volt will be coming to V out, so we can say V out should be equal to direct 5 volt. So yeah, last condition is also fulfilled. Whenever both of the inputs are 1 or logic high, at the output we are going to get 5 volt or logic 1. Yeah, let us now start with resistor transistor logic. RTL. So first we are going to build a NOT gate using RTL. So if you remember from your previous lecture, in one of the circuits we try to find out the voltage transfer characteristics or voltage transfer curve. So we will try to do similar kind of thing here, because the circuit we saw there, this was actually a NOT gate built using RTL logic. So let us try to draw the circuit first. Again we will do that here. So we had this resistor and we had this voltage source of 5 volt. Let us call that VCC. VCC equals to 5 volt, and we have the value of RC is equal to 5 kilo ohm, and then we have this NPN transistor here, and we got the output from here, right? V O was the output. We had another base resistor here, then this is the input VI. Base resistance RB was 150 kilo ohm, and this was directly connected to ground. So this was the circuit, and this transistor was named QN. Some of the parameters were mentioned there for this case, like this is an NPN transistor, so NPN parameters were VBE on equals to 0.7 volt. So which is basically, we have two different junctions here. base to emitter junction, and another one is collector to base junction. So sometimes the junctions are forward biased, reverse biased. So we are talking about this junction here. Whenever base to emitter junction is forward biased, at that condition we are assuming the voltage should be 0.7 volt, similar to constant voltage drop model. We are also assuming another thing. Whenever we are in saturation, so VCE on, or sometimes called VCE in brackets SAT, that value should be equal to 0.2 volt. So whenever both of the junctions are forward biased, that is the condition when the transistor is saturated, right? At that condition, from this collector to this emitter, the voltage we are going to get, the voltage difference we are going to get is should be equal to 0.2 volt. That is our assumption, right? And also another parameter will be given, that is the value of beta 120. That was the value we saw earlier. Now actually this circuit we are seeing here, this is actually an implementation of NOR gate using RTL. So if you give a logic high here, you are going to get a logic low here, and if you give a logic low here, you are going to get logic high. That is the thing we will try to discuss here. So for that we will try to again repeat our discussion we had in that lecture. So how for each of the condition, how if you increase the voltage here at Vi from 0 volt up to a higher voltage, how the output behaves, that is the voltage transfer characteristics. We will try to draw a graph where in the x-axis we will have the independent variable Vi, and with the change of Vi, how VO or V out is changing, that will be plotted in vertical direction. So for that, let us start with a very low voltage of 0 volt. Okay, so what will happen whenever we have a voltage value of Vi which is less than or equal 0.7 volt? For that case, we will see that if we have given a voltage that is less than 0.7 volt, we are never going to get the appropriate voltage at this node, right? We need at least 0.7 volt here at base terminal for this junction base to emitter junction to be forward biased, because emitter is connected with ground, so it should be at least 0.7 volt higher than emitter. So if we are at a voltage lower than 0.7 volt, obviously that will not happen, and because of that we have two different currents here. In this path the current going is called IB, and in that path the current going through is called IC. So because we don't have enough voltages for this particular junction to be forward biased, that means no current will flow through this path, right? And IB should be equal to 0, and if IB is equal to 0, IC we know is equal to beta IB, so IC should also be 0. If that is the case, the current that is going through this path should be 0, and the voltage drop across this resistance, which is ICRC, this should also be equal to 0. So if we want to find out the value of V0, it should be equal to the VCC, the supply voltage we are giving, minus the voltage drop here, so ICRC, and we know ICRC should be equal to 0, so V0 should be equal to what? Directly VCC, or also we can say plus 5 volt. So at this condition, whenever we are at a voltage which is less than 0.7 volt at Vi, what we are going to see is at the output V0 will be directly 5 volt. This is one condition, right? Now let us look at the next condition when we increase the voltage from 0.7 to a higher voltage. So when we start from 0.7 volt, we will see gradually we will have enough voltage at the base terminal here for this junction to be forward biased, right? So we are talking about a condition when V1 is higher than 0.7 volt. So we will try to increase from there and try to understand what happens to the circuit and also at the output, right? So I mean, whenever we have higher voltage than 0.7 volt at this Vi, obviously this think this junction will be forward biased. If junction is forward biased, current can flow from this Vi path to the ground, right? So if that is the case, we can use KVL to find out the value of current here. So because at this point we are saying we are going to get 0.7 volt, what we can say, Vi minus 0.7 divided by the resistance here should be equal to the current we are getting right now, right? So Ib should be equal to what? Ib should be equal to Vi minus 0.7 divided by Rb. Okay, and using that we can also find out other parameters, like we know IC should be equal to beta Ib. So we can say beta, then put this value, so Vi minus 0.7 divided by Rb, right? And from that also we can find out the value of V0, because V0 is equal to what? VCC minus ICRC, and we can put the value of IC here. If we do that, we are going to see that V0 is equal to VCC minus beta V1 Vi minus 0.7 divided by Rb, and we have also Rc. So this is the equation we are getting after going through all of these things. Now you have to understand we are in active mode now, because this junction, this base to emitter junction is forward biased now. We are in active mode. Because of that, Ib current is flowing, and because of Ib current, proportionally a current IC will be flowing through there based on the value of beta, and based on that we are going to get V0. You see, as we increase the value of Ib, IC will increase, as well as ICRC, or the voltage drop, will increase, and that will reduce the amount of voltage we are getting at V0. We will try to discuss that later on, but just try to understand one thing. The equation we are seeing here for this active mode, this is actually a straight line, and more specifically a straight line which has negative slope, because you know we know that whenever we have a straight line, it has a format like this: y is equal to mx plus c, and m is the slope and c is the constant. So if you try to simplify this equation into this type of format, V0 is equal to actually y, and Vi is equal to the x, right? So we can do that. So basically what is happening, V0 equals VCC minus beta RC Vi divided by Rb, and also plus beta RC into 0.7 again divided by Rb, right? So this is the thing we are getting. Now here this thing we can just put it here also, plus VCC, and remove that for our convenience, and also write Vi in blue color so that we can understand which are the independent and dependent variables here. So Vi, right? So compare this equation, this particular equation, with this one. Okay, so this is y and this is mx. So this particular portion is the slope, and we have a negative sign. Whenever we have negative sign here, that means this straight line will have negative slope, and this whole thing is a constant c. So just try to remember this portion for now. We will try to take help from this equation whenever we try to draw the voltage transfer curve. Now for the last case, what we are going to do, we will try to find out what happens afterwards. So we are trying to increase the value of voltage Vi here starting from 0.7. So I discussed about the fact that whenever you are increasing the value of Vi, so that is actually increasing the value of Ib also, you know. So because as Vi is increasing, still we are going to assume that the voltage we are getting at this node, base node, this is 0.7, all the values are fixed. So as you increase this value, as you increase the value of Vi from 0.7, Ib should also increase, right? And as you increase Ib, because IC is equal to beta Ib, IC should also increase. If IC increases, look at this particular portion, that means this resistance, the voltage drop we are getting, this should also increase because ICRC is equal to the voltage drop. That means the voltage drop ICRC is increasing. Now because V0 is equal to the voltage we are supplying here minus the voltage drop here, so obviously V0 will keep reducing as this ICRC is increasing, right? So we can say ICRC is increasing but the value of V0 is reducing. So what happens, it when we keep increasing and increasing this Vi value, at certain point we will reach saturation of this transistor, because you know for saturation condition VCE should be 0.2 volt. VCE is this collector to this emitter voltage. V0 is can be called this VCE because V0 is at collector terminal and this one is connected to ground. So if V0 reduces and reaches to a value of 0.2 volt, that is the saturation region. So using that understanding, right now we will try to formulate what is the value we are going to get for input. Okay, so yeah, so whenever we have this kind of condition, so I mean whenever we have saturation, we know one thing, that is VCE should be at 0.2 volt, but what is the required Vi or input voltage, we still don't know. That is the problem. So what we can do, we can still use this equation we have found out for active region. It is still valid for saturation region as well, but here you know one parameter we directly know is the value of V0, because V0 can be considered as VCE on for saturation condition. So V0 should be 0.2 volt, and just by putting this value we can find out the value of Vi. So let us try to do that. So V0 equals to VCC minus beta RC divided by RB multiplied with what? Vi minus 0.7. So let us try to put all the values. We know the value of V0. This is for the condition whenever we have saturation, right? Saturation means VC on is equal to 0.2 volt, or V0 should be also equal to 0.2 volt. So VCC is equal to 5 and beta value is 120, RC value is 5K, RB value is 150K, and finally we need to find the value of Vi. So let us try to simplify all of these things and try to find out the value of Vi. So after calculating everything, what we are going to see is the value of Vi should be equals to 1.9 volt. Okay, so this is when we have saturation, that means V0 is equal to 0.2 volt, and this is for saturation condition, right? Now using all of this value, we will try to build or draw the voltage transfer curve for this particular circuit. So after getting all of this, we can finally look at the voltage transfer curve. So this was the voltage transfer curve found out from all of these steps we have done. So just try to understand that we started from 0 up to 0.7 volt, and we saw that that was cutoff region, and in that region no current was flowing through IB. Because of that, no current through IC, and because of that, this VCC direct 5 volt was coming to V0. So that's why in this region we are getting 5 volt. Then after increasing the voltage starting from 0.7 up to a higher value, we saw that this junction was forward biased. Because of that, current was starting to flow, IB was increasing. Because of that, IC was also increasing, and because of that, ICRC was increasing. If ICRC was increasing, what will happen? This voltage drop will reduce the amount of voltage we are getting across V0. So that's why you see in this region gradually the value of output V0 was decreasing. This is the active region, right? And up to how much? Whenever we reach saturation, at that point we see that the voltage is not reducing anymore. So V0 is fixed at 0.2 volt. So we just by taking that value, V0 is equal to 0.2 volt, we try to calculate the value of VI, input voltage, and that came out as 1.9 volt. So for whole this region, that means if we try to increase more from 1.9 volt up to a higher value for the input, still we are going to see that the output is not changing. It is fixed at 0.2 volt. So this is saturation region. Now how this will work as a NOT gate? To understand that, just understand the fact that whenever we are providing a voltage from 0 up to 0.7 volt, a very low voltage closer to 0 volt, so logic 0, what we are getting? We are getting a fixed output of 5 volt, so which is logic high. So it is inversing the input. And similarly, starting from 1.9 volt up to 5 volt, if we give this amount of voltage at the input, what is happening? Because of that, we are getting a very low output at V0, right? So again, this is can be considered as logic high at the input, and because of that, we are getting the inverse input of logic 0, which is 0.2 volt, right? So in this way, this is working as a NOT gate. Now if we try to define the parameters we have learned before for logic levels, like VOH, VIH, VOL, and VIL, how can we define those in this voltage transfer curve? To understand that, just let us look at the input first. So for logic low, this is the valid region, right? For logic low input, and this is the valid region for high input. And we know that the maximum possible voltage for logic low, we have that the logic gate can interpret as logic low, that is actually VIL. So this is the maximum value allowed for the input, right? So that it can recognize. So 0.7 actually can be called VIL here, and also similarly this is the region or allowed region for logic high input. So the minimum value of that should be VIH, right? So we have learned that VIL is equal to what? 0.7 volt, and VIH is equal to 1.9 volt, right? And if you let us talk about the output. So for output, the allowed range of voltage for logic high is just this 5 volt. There is no range, right? Directly this region is actually for logic high, and this region from 0.2 to 0 volt, this is allowed range for logic low for the output, right? This is the accepted range of voltages for logic low for the output. So if that is the case, again we can define VOH as 5 volt, because this is the minimum allowed voltage for the output pin of logic gate, and 0.2 should be VOL. This is the maximum value allowed for the logic gate output. So in this way you can understand. So VOH is equal to what? 5 volt, and VOL should be equal to 0.2. And using these values we can also find the value of noise margin, right? If we try to draw the same thing we had drawn earlier in our previous lectures, so we had logic levels defined in terms of 0 to 5 volt, both for input and output. So let us try to do that. So this is for output, let's say, and this is for input. Okay, yeah. So this value here, this is 5 volt, and this value you see here, this is 0 volt, right? And this is for output of logic gate, and this is for input of logic gate. If that is the case, we can directly from these values we can draw that, right? VOH should be here, right? VOH, and VIH should be where? If I divide this into 5 different region, 1 2 3 4, maybe, yeah. So 1 2 3 4 5, that is 5 volt. So maybe here, right? Maybe here we are going to get VIH, right? And for VOL is here, so maybe very close to 0 voltage. So this is VOL, and which is 0.2 volt, right? 0.2 volt. This is actually 1.9 volt, and you know this is 5 volt obviously, and VIL should be 0.7 volt. So maybe here VIL 0.7 volt, right? So using this you can understand, you can find out the noise margin as well. So for the high case, the noise margin should be from here to here, right? So the amount of voltage we are getting from here to here, this amount of voltage is actually noise margin for high, or we can say VNH. VNH is equal to VOH minus VIH, or in our case 5 minus 1.9, which is equal to what? 3.1 volt, right? And if we try to find out VNL, it should be equal to the difference of between these two voltage, IL and OL. So that will be VIL minus VOL. So 0.7 minus 0.2 equals to 0.5 volt. So in this way we can find out the logic level parameters as well as the noise margin of our particular RTL circuit. Yeah, that's it for this lecture. Thank you.